Hi guys, welcome back to the channel. In today's lecture, we are going to discuss one problem on gable frame structure, in which we will be analyzing this gable frame by using the concept of slope deflection method, right? So we already discussed about slope deflection method in detail. Okay, now we need to analyze. We will use the concept of slope deflection method to analyze this frame, right? This is the gable frame structure. As you can see that here we are having these are two sloping sides, and this is the apex point, right? And this type of a structure has industrial use basically, and these type of structures are basically used where the span required is more, where the span required is large. Here you can see that the clear span is basically 7.5 meter. Okay, in those type of cases we will be using this type of structure. Okay, so we need to analyze this structure by using this concept of slope deflection method. And before in slope deflection method, this initial thing which we need to find is the kinematic indeterminacy of this frame structure, right? Because the kinematic indeterminacy is basically the unknown displacement, right? And with the help of the unknown displacement, with the help of the unknown displacement, we will be calculating the internal forces generating in the members, right? So now let us first calculate. First step is to calculate kinematic indeterminacy of this frame. Okay, this is the most important part in this gable frame structure. Okay, now, and we are assuming that members are inextensible. Members are inextensible. Which means that along the member we are not allowing any deformations, right? So now if we come to this frame, at this point A, this is A, this is B. Okay, at A point the theta will be 0 and delta will be 0. Why 0? Because this is a fixed support. Okay, and similarly at E point, at E support, which is fixed support, theta will be 0 and delta will be 0, right? Now let us come to this B point. This B, this C, and this D point. Okay, so kinematic indeterminacy we always defined at nodes. These are basically our node points, right? So at B, I will be having one theta B, right? One deflection delta B. Okay, and that deflection will be perpendicular to this member. This thing we have already discussed, right? And there will be, let us suppose, if there is any vertical deflection at this point. So vertical deflection won't be there. Why? Because this member we are considering inextensible, so this deflection won't be there. Okay, so at B point we will be having two displacement, which is delta B and theta B, right? Now let us come to this C point. Okay, at C there will be one theta C, one delta C, and one delta D. Okay, at this point. Again at this theta D point, this will move in forward direction, and this is equals to delta D, and there will be one rotation theta D. Okay, this delta V and this delta D won't be equal. Okay, right? So now this here also the axial deformation is basically 0, right? For this delta D in vertical direction, delta D vertical is 0 basically. Here delta B vertical is 0. Okay, because we are not allowing, because these members we are considering as inextensible, so this D point will always move perpendicular to this member. Okay, now the situation is like this. If let us suppose this is this is our top portion. This portion is moving by delta B. This portion is moving by delta D amount. Okay, and this we are considering delta C vertical this is delta C horizontal. Okay, now you can see that this is theta B and this is theta D, here theta C, right? Now you can see that total number of deflection here, total number of, I'm just talking about these displacement 1, 2, 3, 4. Okay, these displacement I'm not considering now this rotation here. Okay, I'm just taking this 4 displacement. So these 4 displacement, okay, and you can see that these are connected by 2 inextensible members. Okay, so number of independent displacement will be 4 minus of 2. Okay, what I meant by that is that these 4 displacement, this delta B, this delta C, this delta CH, this delta CV, and this delta D, I can represent I can represent these 4 displacement with the help of 2 primary displacement, okay, or with the help of 2 independent displacement. So here in this thing you can get through this thing total number of displacement, which is this displacement in horizontal and vertical deflection, is basically 4. Okay, and these are connected by two inextensible members. So number of independent displacement will be 2, right? So here what I will do, I am considering this delta B and this delta D as an independent displacement. Okay, and I will represent this delta C vertical and this delta C horizontal in terms of these 2 displacement, right? Because if I know these 2 displacement, this delta B and delta D, I can easily derive this delta D and delta C, delta C vertical here and delta C horizontal, right? So if someone asks you what is the kinematic indeterminacy of this frame, this will be equals to theta B, theta C, theta D, delta B and delta D. Okay, so this is 5. So kinematic indeterminacy of this frame is 5 basically. Okay, displacement will be here at this point, but that displacement we will find with the help of these 2 unknowns. Okay, if you are unable to think like this, you can also think, you can also consider, suppose this is a frame over here. Okay, so here let us suppose we are assuming this is A, this is B, this is C, and this is D. This is, let us suppose this is delta B. At this point we are having delta C, right? So these 2 displacement, this delta B and delta C, are connected by this single inextensible member. Okay, so total displacement is 2, so 2 minus 1 will be 1. So you can see that this delta B and delta C are basic, so the independent displacement is 1. So this delta B and delta C we can represent with the help of common displacement, which is delta. Okay, because this member is inextensible, right? Same concept by using the property of inextensible member, we can write these 2 displacement in terms of these 2 independent displacement. Okay, so basically these are our independent displacement, which is equals to kinematic indeterminacy, right? Now next step is to find the relation between. Now let us consider one other frame, Gable frame. Okay, now let us suppose if this Gable frame is symmetrical one. Okay, if this Gable frame is symmetrical and there is a load acting at the center point, which is, let us suppose, P load, right? So as you can see that this frame is basically symmetrical, so the response of this Gable frame will also be symmetrical. Okay, so if I am considering this is delta, so this will also be delta, right? And at this portion cannot move. This cannot move this side, right? Cannot move this side or this side, because the response should be symmetrical. So this point will be having displacement in this direction, which is, let us suppose, delta P vertical. It cannot move in horizontal direction because this response should be symmetrical, right? So here you can see that the primary displacement is basically these two displacements are basically equal. So number of and this delta P I can write in terms of this delta, right? So if someone asks what is the kinematic indeterminacy of this frame, is this basically this delta. Let us suppose this is A, this is B, this is C, this is D, this is E. So kinematic indeterminacy will be delta B, theta B, delta, theta C, and theta D. Okay, so this is kinematic indeterminacy is 4. So kinematic indeterminacy is basically the unknowns. Okay, displacement will be there. This vertical displacement will be there. But this displacement we can find with the help of this delta component, because we can use the property of the member inextensible property, because these two members are basically inextensible. Okay, so we can represent this displacement in terms of this displacement, right? That thing we will see now. So this is the case basically. So we know that this portion is moving by delta B amount, right? And this portion is moving by delta D amount. Okay. Now what we will do, we will displace this portion, and this is connected by these two columns. Okay, now we will displace this structure like this, that there should be the members, we will use the concept of that there should be, means that there should be no axial deformation along the member. Okay, so now let us suppose this point comes here, or you can say that. What we will do, first we will draw a parallel line to this member. Okay, and let us suppose this is also delta B. Okay, why we are doing this we will see later. Okay, and suppose this delta D this is again, this is parallel to this and this is parallel to this, right? Okay, this total distance is basically delta D. Okay, now what we will do, we will draw a perpendicular over here. Okay, and similarly from this side we will draw another perpendicular. Okay, so these two perpendicular will meet at a point. So this is the way your point, this C point will come here. Okay, this C, and let us denote it by C dash, something by C dash. Okay, so this C point will move like this. Okay, and why now we did these things because we want our displacement like this, that there should not be any axial deformation in the member. Okay, so first what we did, we give this point of delta B displacement in this direction, and similarly delta B displacement in this direction. Okay, up to here there is no axial movement, right? Then again we drop a perpendicular over here. Okay, we drop a one perpendicular over here, and similarly from this side also we dropped one perpendicular. Okay, and both the perpendiculars meeting at point C dash, which is the display, this is the point where the C point will displace. This joint will displace and come to this point C dash. Okay, now you can see that we are not allowing the axial deformation along the member. Okay, this movement, from here to here, there is no axial movement there is no axial deformation in the member. Similarly, from this portion to this portion, there is not any axial deformation in the member. Okay, and the displacement which will be responsible, the displacement which will be responsible for generating moment in this portion will be this displacement. Okay, will be this displacement. Okay, this is C dash. Basically, this distance will be delta D minus of delta B, right? This is delta D minus of delta B. And we need to find this angle, basically. So this angle we can find like this. We can drop one perpendicular. This angle is alpha. This angle is 90 minus of alpha. So this angle will be again 90 minus of alpha. So this is 90 minus of alpha. Similarly, this angle will be 90 minus of beta, and this angle will be alpha plus beta. Okay, you can use the concept of trigonometry over here. Okay, so guys, now you can see that now we basically required these two displacement. Okay, this figure is enlarged view of this figure, this point. Okay, so we need to find basically these two displacement will be responsible for generating moments in this portion. Okay, in this for this member, the sway will be due to this displacement. Okay, the moment generated due to sway will be due to this displacement, these two displacement. Okay, these two displacement, right? So now let us suppose if this is delta 1 dash, or you can see that, or you delta C dash 1. Okay, this is delta C dash 2, right? So I can write using the concept of sine law, sine alpha plus beta over में delta D minus of delta B, right, equals to sine 90 minus of alpha delta C2 dash equals to sine 90 minus of beta over my delta C dash 1. Okay, so we have what we did over here is that we have established the relation between this delta C1 dash and delta C2 dash, okay, with the help of this sine law. Okay, and basically the unknowns are delta D and delta B. Okay, so with the help of these two displacement delta B and delta D, we are writing the equation for these two displacement components, okay, by using the sine law, right? So I hope I made my point clear over here, right? So now let us solve this problem. Okay, this is the most important part, how this point is coming down, right? How we did this thing. Okay, this is the most important part. So now let us analyze this problem, write the slope deflection equations. Okay, so basically this point, this displacement is this displacement, and this displacement is basically this displacement, right? Now we will be forming slope deflection equation. Now let us consider this MAB. MAB will be equals to M of AB plus 2EI over may L. L is 3.6 into may twice theta A plus theta B, and this joint is displacing perpendicular to this member. Okay, so this is nothing but 3 delta B over may L. L is what? L is basically 3.6. Okay, right? So this is the first equation for MAB. So I can write this will be 0. This theta A will be 0 because this is a fixed slope, right? So now MAB will be equals to this is 2 divided by 3.6. This is 0.55 EI theta B minus of 2 into 3 divided by 3.6 divided by 3.6. So this is 0.463 delta B. Okay, so let us term this as equation A. So I am writing this thing over here. So MAB is basically 0.55 EI theta B minus of 0.463 EI delta B. Okay, so this will be EI delta B, right? Similarly, I can write the equation for MAB. MBA will be 0. This will be MFBA plus 2EI over 3.6, right? This is twice theta B plus theta A minus of 3 delta by L. L is what? 3.6. Negative sign is because this movement when it is moving like this will be resulting in generation of anti-clockwise movement. Okay, that's why we are taking negative sign over here. Okay, this thing we have already discussed in detail, right? So if you solve this equation, so it will be 0.55 into 2. This is 1.1 EI theta B minus of 0.463 EI delta B, right? So this is MBA. So MBA will be 1.1 EI theta B minus of 0.463 EI delta B. This is A, this is, let us suppose, B. Okay, so we have established the relation for this column, basically this AB column. Now for this member BC. So we have already discussed this is moving like this. Okay, and this is delta C dash. So you can see that when this portion is all moving by delta B, this is moving by delta B. Okay, we have assumed, right? So there won't be any force, there won't be any generation of force over here between these two movements, because this is moving parallelly to this, right? Now the moment will generate due to this delta C dash 1 movement, right? So basically I need to write MBC is equals to MFBC plus 2EIL. L is what? L we need to calculate this length. Basically this length we will be calculating. Okay, this is 21.8 So this is 4.5. So we will be using cos 21.8 into 4.5. So this is 4.5. So you need to calculate this length basically. So this will be equals to cos this distance we will be using cosine law. So 4.5 divided by cos 21.8. Right, this is 4.8485. You can write 4.85. This distance is 4.85, right? So this length is basically 4.85. This is twice theta b plus theta c minus of 3 delta c dash c1 dash over my L. L is what? 4.85, right? So now let us calculate. Now we will be using. I will be using this relation over here. Okay. From the sine law, delta d minus of delta b over my sine alpha. Alpha is 21.8 plus beta is 30.96 is equals to delta c dash 1 over my sine 90 minus of 30.96. Okay. So I will be using this relation over here. So 1 divided by sine 21.8 plus 30.96 into sine 90 minus 30.96. 1 divided by sine 21.8 plus 30.96 into sine 90 minus 30.96. So delta c1 dash, delta c dash, this is delta d minus delta b into 1.077 is equals to delta c1 dash, right? So here this term is 0, no friction moment will be there, right? So my equation will be, this is twice 4.85 twice theta b plus theta c minus of 4.85. Delta c dash is basically 1.077 into delta d minus of delta b. Okay. So if you solve this equation, this will be 2 into 2 divided by 4.85. So this is 0.824 theta b plus 2 divided by 4.85. This is 0.412 theta c, right? And this will be minus 3 into 2 into 1.077 divided by 4.85 square. So this is 0.274 delta d, and this is plus, then this will be plus 0.274 delta b. Okay, so this is the equation for MBC, right? Okay, so you need to basically understand this movement basically. Okay, that is the main part in this problem. So MBC will be 0.824 theta b plus 0.412 theta c minus 0.274 delta d plus 0.274 delta b. Okay, so MBC is 0.824 theta b plus 0.412 theta c minus 0.274 delta d plus 0.274 delta B. Let us term this as equation C. Okay. Similarly, we will write the moment generation will be negative. Okay, this value will be negative. Why negative? Because this is moving like this. So there will be anti-clockwise moment generated due to this movement. Okay, so that's why we kept negative sign over here. Right. Now similarly, we will write the equation for MCB. Okay, MCB, and it will be equals to 0.824 theta C plus 0.412 theta B. This will be same, minus 0.274 delta D plus 0.274 delta B. Okay, so this will be our equation for MCB. So MCB will be equals to 0.824 theta C plus 0.412 theta B minus 274 delta D plus 0.274 delta B. Let us term this as equation number D. Okay. So we have write the equation for this BC member. Okay, in which we have established the force displacement relationship. Basically, these are our force displacement relationship where we are representing end moments in terms of displacement. Okay, so this is done. So now let us come to this member CD. Okay, so we have seen this was our movement basically. Okay. So this now we need to find this displacement basically, this portion. Okay, this displacement we need to consider, and this is equal to this thing we have already discussed, right? So now again we will be establishing the force displacement relationship for this CD member. Okay, so I can write MCD will be equals to MF CD plus 2EI L. We need to calculate for this portion, and again this we will be using cosine law. So 3 divided by cos 30.96. So this is basically 3.499. So I can write it as 3.50. Okay. So this is 3.5 twice theta C plus theta B minus of 3. This is delta C2. This is delta C dash 2 over L. L is what? 3.50. So now you can see that this portion is coming like this portion is coming down. Okay. So what are the moments? Moments will be clockwise moment will be here. Okay, clockwise moment will be induced. So this will be positive basically, right? When this portion is coming here, the moment induced will be clockwise at the ends, right? So this will be positive. So again, we need to establish the relationship between this delta C2 dash and this delta D minus delta B. So I can write delta D minus of delta B over my sine 21.8 plus 30.96 is equals to delta C dash 2 over my sine 90 minus of 21.8, right? So if you solve this thing, so 1 divided by sine 21.8 plus 30.96, this is into sine 90 minus 21.8. So this is 1.166 delta D minus of delta B is equals to delta C dash 2. Okay. So again, in place of this delta C2 dash, we will write this expression. So this term is basically 0. So this will be 2 EI over my 3.5. This is twice theta C, theta B, no, theta D plus 1.166 delta D minus of delta B over my 3.5. Okay. So if you solve this thing, it will be 4 divided by 3.5. So this is 1.142 theta C plus 2 divided by 3.5. This is 0.571 EI theta D. Okay, there will be EI terms will be there. I forgot to write EI, EI, EI and EI. Similarly for here also EI, EI, EI and EI. Right? So this is nothing but plus this is 3 into 2 into 1.166 divided by 3.5 square. This value is 0.571 delta D minus 0.571 delta B EI. Right? So MCD will be equals to 1.142 EI theta C plus 0.571 EI theta D plus 0.571 delta D minus 0.571 delta B. So this is equation number E. Okay. Similarly, we can write this equation for MDC. MDC will be equals to, it will be similar. These coefficient will interchange basically. So it will be 1.142 EI theta D plus 0.571 EI theta C plus 0.571 delta D minus 0.571 delta B. This is equation number F. Okay. So we have write the equation for this CD member. Now next step is to write the equation for this DE member. Okay. So this portion, this D point, this D joint is moving like this, delta D will be here. Okay. So there will be anti-clockwise movement again. So I can write MDC equals to MF DC plus 2EI. L is what? L is 3.6 twice theta D plus theta E minus of 3 into delta D over my 3.6. Right? This is 0. This is 0, fixed support. So MDC will be 4 divided by 3.6. This is 1.11 EI theta D minus of 2 into 3 divided by 3.6 whole square. So this will be 0.463 delta D. Right? Similarly, this is MED will be equals to 1.11 divided by 2. So this is 0.55 EI theta D minus 0.463 EI delta D. Right? So MDC we have write MDE. This is equals to 1.11 EI theta D minus 0.463 delta D. Right? Similarly, MED will be 0.55 EI theta d minus of 0.463 delta d. This is equation number G, this is H. Okay. So now you can see that we have established this force displacement relationship. Basically, this is force displacement relationship, right? After establishing the force displacement relationship, we will be using the concept of joint equilibrium, where we will be obtaining some equation correspond to this displacement. Okay, so here we are saying that we have 5 unknowns, right? This 5 total unknown displacements are basically 5. So somehow we need to find 5 equations. We need to form 5 equations. Okay, so next step is to form this joint equilibrium equation.